Chapter 3, Section 2 deals with gravity. What is gravity? Gravity is an attractive force between any two objects that depends on the masses of the objects and the distance between them. The illustrations indicate that the attraction of gravity is greater between these two objects than it is between these two objects. And in this graphic, the attraction of gravity is greater between these two objects that are closer than these that are farther apart. Gravity is one of the four basic forces. The other basic forces are the electromagnetic force, the strong nuclear force, and the weak nuclear force. The law of universal gravitation. Isaac Newton formulated the law of universal gravitation, which he published in 1687. This law can be written as the following equation. The gravitational force, they spelled it wrong, equals a constant g times the mass of the first object times the mass of the second divided by the distance squared. In this equation, g is a constant called the universal gravitational constant. We'll take a look at that in a minute. And d is the distance between the two masses, m1 and m2. The law of universal gravitation enables the force of gravity to be calculated between any two objects if their masses and the distance between them is known. According to the law of universal gravitation, the gravitational force between two masses decreases rapidly as the distance between the masses increases. So, an example of that would be if you blast off to the moon, there is still the attraction of gravity between you and the Earth, or you and your friend, but it diminishes or decreases as the distance increases. No matter how far apart two objects are, the gravitational force between them never completely goes to zero. Because the gravitational force between two objects never disappears, gravity is called a long-range force. In the 1840s, the most distant planet known was Uranus. The motion of Uranus, calculated from the law of universal gravitation, disagreed slightly with its observed motion. It didn't follow the prescribed path. Some astronomers suggested that there must be an undiscovered planet affecting the motion of Uranus. Using the law of universal gravitation and Newton's laws of motion, two astronomers independently calculated the orbit of this planet. As a result of these calculations, the planet Neptune was found in 1846. Earth's gravitational acceleration. When all forces except gravity acting on a falling object can be ignored, the object is said to be in free fall. Close to Earth's surface, the acceleration of a falling object in free fall is about 9.8 meters per second squared. This acceleration is given the symbol g and is sometimes called the acceleration of gravity. Close to Earth's surface, the acceleration of a falling object in free fall is about 9.8 meters per second squared. This acceleration is given the symbol g and is sometimes called the acceleration of gravity. By Newton's second law of motion, the force of Earth's gravity on a falling object is the object's mass times the acceleration of gravity. Weight. The gravitational force exerted on an object is called the object's weight. Because the weight of an object on Earth is equal to the force of Earth's gravity on the object, weight can be calculated from this equation. Weight in newtons, and I want to emphasize again that if I'm asking you what a weight is in this class, and especially in this chapter, weight is given in newtons. It's a force. It equals the mass of an object in kilograms, the SI units, times the acceleration of gravity, which is 9.8 meters per second squared. 9.8 meters per second squared. Weight and mass are not the same. Weight is a force. Weight is a force, and mass is a measure of the amount of matter an object contains. Weight and mass are related, however. Weight increases as mass increases. The weight of an object usually is a gravitational force between the object and the earth. The weight of an object can change depending on the gravitational force on the object. This table shows how various weights on Earth would be different on the Moon and some of the planets. You can point out your weight in newtons on Earth is only 12 newtons on the Moon. And it would make sense that because Jupiter is so many more times bigger than the Earth, that Jupiter, your weight on Jupiter would be more than your weight on Earth. Let's go back to that table one more time here. Oops. Once again here with this table, I don't expect you to memorize this. And one important one to realize is that the weight, your weight on the Moon is about 1/6 of your weight on Earth. Weightlessness and free fall. You've probably seen pictures of astronauts and equipment floating inside the space shuttle. They're said to be experiencing the sensation of weightlessness. However, for a typical mission, the shuttle orbits Earth at an altitude of about 400 kilometers. According to the law of universal gravitation, at 400 kilometers altitude, the force of Earth's gravity is about 90% as strong as it is at Earth's surface. So an astronaut with a mass of 80 kilograms still would weigh about 700 newtons in orbit, compared with a weight of about 780 newtons at Earth's surface. So what does it mean to say that something is weightless in orbit? When you stand on a scale, you're at rest and the net force on you is 0. The scale supports you and balances your weight by exerting an upward force. The dial on the scale shows the upward force exerted by the scale, which is your weight. Now, suppose you stand on a scale in an elevator that is falling. If you and the scale were in free fall, then you no longer would push down on the scale at all. The scale dial would say you have 0 weight, even though the force of gravity on you hasn't changed. A space shuttle in orbit is in free fall, but it is falling around Earth rather than straight down. Everything in the orbiting space shuttle is falling around Earth at the same rate, in the same way you and the scale were falling in the elevator. Objects in the shuttle seem to be floating because they're falling with the same acceleration. Projectile motion. If you've tossed a ball to someone, you've probably noticed that thrown objects don't always travel in straight lines. They curve downward. Earth's gravity causes projectiles to follow a curved path. Horizontal and vertical motion. When you throw a ball, the force exerted by your hand pushes the ball forward. This force gives the ball horizontal motion. No force accelerates it forward, so its horizontal velocity is constant if you ignore air resistance. However, when you let go of the ball, gravity can pull it downward, giving it vertical motion. The ball has constant horizontal velocity, but increasing vertical velocity. Gravity exerts an unbalanced force on the ball, changing the direction of its path from only forward to forward and down. The result of these two motions is that the ball appears to travel in a curve. If you were to throw a ball as hard as you could from shoulder height in a perfectly horizontal direction, would it take longer to reach the ground than if you dropped the ball from the same height? And we did this demo in class already. Surprisingly, it wouldn't. Both balls travel the same vertical distance in the same amount of time. When a ball enters a curve, even if its speed doesn't change, it's accelerating because its direction is changing. When a ball goes around a curve, the change in the direction of the velocity is toward the center of the curve. Acceleration toward the center of a curved or circular path is called centripetal acceleration. According to the second law of motion, when a ball has centripetal acceleration, the direction of the net force on a ball also must be toward the center of the curved path. The net force exerted toward the center of a curved path is called a centripetal force. When a car rounds a curve on a highway, a centripetal force must be acting on the car to keep it moving in a curved path. The centripetal force is the frictional force or the traction between the tires and the road surface. Anything that moves in a circle is doing so because a centripetal force is accelerating it toward the center. Imagine rolling an object tied to a string above your head. The string exerts a centripetal force on the object that keeps it moving in a circular path. In the same way, Earth's gravity exerts a centripetal force on the moon that keeps it moving in a nearly circular orbit. This completes the lecture notes for section 2. Question number 1, and again, answer the questions and submit your answers on your MyBigCampus site where it says post assignment here. Question 1. Gravity is an attractive force between any two objects and depends on what? Question 2. Which is not one of the four basic forces? Question 3. Which of the following equations represents the law of universal gravitation? That concludes the lecture notes for chapter 3, section 2.